Okay, we are in section 3.2. So we just talked about exponential functions in section 3.1. And now here in section 3.2, we want to talk about logarithmic functions. And there's actually a very special relationship between exponential and logarithmic functions. Because a logarithmic function is the inverse of the corresponding exponential function. So you have to remember what you know about inverse functions. So for example, here we have an exponential function with base b. We just talked about this in section 3.1. Y equals b to the x. Remember, b has to be a positive constant, but it can't be 1. Okay. If you wanted to find the inverse of that, remember what you do to find the inverse? You switch the x's and the y's, right? So this means I'm going to have x equals b to the y, and then solve for y. But solving for y now, you don't know how to do that. So actually, what we have learned over the years is that when I solve this for y, it becomes a special function called the log base b. So log base b of x. So this guy, x equals b to the y, and y equals log base b of x, are two forms telling us the same thing about the relationship between x and y. Okay, so remember, y equals b to the x is an exponential function with base b. If we were switching the x and the y, it's no longer this guy. This is equivalent to this. Okay, and that's what I want you to remember. Okay, so y equals log base b of x is equivalent to x equals b to the y. They say the same thing. So really, when you read this thing, if you're just shown this, what you want to think of this as is this tells us that b, the base, raised to the power y is equal to x. Okay, that helps us figure out what the value of y is at times. So first of all, note that if the base b is equal to e, just like that's called the natural exponential function over here, e to the x, over here that's called the natural logarithmic function. So we don't typically write log e, log base e of x, we write ln of x. Means the natural log, but we'd say ln of x. Means the natural log, which is log base e of x. Okay, in our first example, we want to evaluate log base 2 of 16 equals y. In other words, we want to know what y is. So the easiest way to figure this out is to think about in exponential form, what is this equivalent to? So we always say the base b raised to the right-hand side y. So 2 to the y equals the x value 16. So 2 to the y equals 16, so then we should be able to think about, well, what value of y does that? And I have to take 2 to the 4th power to get 16, so y is 4. Similarly, if I have log base 27 of 9 equals y, then I want to think of that in its exponential form, which is 27 to the right-hand side y, 27 to the power y equals 9. So I know the cube root of 27 is 3, right? So if y were 1/3, I would have 27 to the 1/3 equals 3, but I want 9, so I have to square that. So that means that y would be 2/3, right? 27 to the 2/3 power, which is 27 to the 1/3 squared, or y equals 2/3. All right, inverse properties of logarithms. This is equivalent to saying f inverse of f of x equals x, right? If I know inverses. And this is equivalent to saying f of f inverse of x equals x. So the log base b of b to the x is just x. And b raised to the power log base b of x is just x. So in example 2 here, we want to evaluate log base 4 of 4 to the 5. In other words, 4 to the what equals 4 to the 5. So that one's simple, that's 5. Here I have the base b raised to the power log base b of x. We just shoot x back out as well. So b raised to log base b of x equals x. So 6 raised to log base 6 of 15 equals 15. Now what do the graphs of logarithmic functions look like? The easiest way to know what they look like is to remember that they are the inverse functions of exponential functions, which means that their graphs would be the exponential function reflected across the line y equals x. Because we know that that's what inverse functions look like. They're the reflection of the function across y equals x. So if this is the exponential function for b greater than 1, we know that the exponential function looks like this. Then a logarithmic function for log base b of x when b is greater than 1 would look like this guy. So 0, 1 is on the graph of the exponential function, means that 1, 0 is on the graph of the log function. Same thing with the logarithmic function for base between 0 and 1. We know it looks like this, so it reflected across the line y equals x. The log base b of x function would look like this. Okay? So it's good for you to understand what the general shape of those is, because if I ever want to graph a function like log base 2 of x minus 1, then what I do is I work with log base 2 of x and realize that this is f of x, so this would be f of x minus 1, which means I'm going to shift f of x 1 unit to the right. So we'll just graph log base 2 of x lightly, and then shift that to the right by 1 unit to get log base 2 of x minus 1. Okay, so I'm going to plug in different values of x. So for x equals 1, log base 2 of x. 2 to what power equals 1? Well, that's 2 to the 0. If x is 2, 2 to what power equals 2? Well, that's x equals 1. If x is 4, notice I'm choosing values of x so that 2 to the power equal those easily, nice integer numbers. If x is 4, 2 to what power equals 4? Well, that's 2 squared. If x is 8, then 2 to what power equals 8? Well, that's 3, so 2 cubed equals 8. If x is a half, 2 to what power equals 1 half? Well, that's 2 to the minus 1, right? Because 2 to the minus 1 is 1 over 2, which is 1 half. And 2 to the minus 2 would be 1 over 2 squared, which is 1/4. So if x is a fourth, then y is minus 2, right? The log base 2 of x would be minus 2. So I can plot those values. This is x, y, right? So the value, 1, 0. 1, 0 is this guy, which I know is always on log base b of x. So the point 2, 1, this guy is on log base 2 of x. The point 4, 2 is on log base 2 of x. The point 8, 3, so 8, 3 is on log base 2 of x. The point 1 half minus 1, right? 1 half minus 1 is on log base 2 of x. The point 1 half minus 2 is on 1/4 minus 2 is on log base 2 of x. So I kind of draw in that with a dotted line, and I say to myself, well, shift all of these points 1 unit to the right. So 1/4 minus 2 becomes 5/4 minus 2. 1 half minus 1 becomes 3 halves minus 1. You with me so far? Good. 1, 0 becomes 2, 0, shifting everything 1 unit to the right. 2, 1 becomes 3, 1. 4, 2 becomes 5, 2. 8, 3 becomes 9, 3. And then I connect those, and that is the function that I want. And we could do the same thing with log base 4 of x plus 2. So in other words, I'm going to graph log base 4 of x and shift it 2 units left, because this is like f of x plus 2. Shift it 2 units left. So log base 4 of x, I want to pick values of x that are easy to figure out what y should be, right? So x equals 1 is always on the graph. We know that. So that's when y is 0. 4 to what power equals 1? That power is 0. 4 to the 1 power equals 4. 4 to the 3 halves power equals 8, right? 4 to the 1 half is 2. 2 cubed is 8. 4 to the minus 1, 1/4. 4 to the minus 2, 1/16. Pick values that are easy to do. So that's these guys, these open circles. And then I'm going to shift 2 units left. So 2 units left, 2 units left, 2 units left, 2 units left, 2 units left. This is now the log base 4 of x plus 2. So notice what happened. Shifting everything 1 unit to the right in example 3 means my domain became 1 to infinity instead of 0 to infinity. And shifting everything 2 units to the left for log base 4 of x plus 2 means my domain is now minus 2 to infinity instead of 0 to infinity. And that's the end of section 3.2.